Hi, my name is Daily. I'm presenting our work, Incremental Learning of Retrievable Skills for Efficient Continual Task Adaptation. This paper is the latest research and will be presented at NeurIPS 2024, a top-tier conference in the field of artificial intelligence and machine learning. I am currently a visiting scholar at Carnegie Mellon University, focusing on artificial intelligence research. I'm also pursuing my PhD in computer science at 성균관 University, where I work in the CSI Agent Lab under the guidance of Professor Woo. I completed my bachelor's degree in computer science and engineering at SKKU. Let's start today's presentation with a short video. This video showcases the latest trends in home robots. It's quite impressive. These models are typically trained on large multimodal datasets that include vision observation and language instructions and action modalities, allowing them to perform a variety of household tasks. However, they often face challenging situations due to the changes in their home environment. For example, new furniture or the need for new skills of novel objects, which cannot be addressed using previously learned knowledge alone. The paper I'm presenting today proposes a solution to tackle this problem. Let me briefly introduce the preliminaries necessary to understand this paper. These concepts provide the foundation for the methodology and explain the problem scenarios the paper aims to address. Now, let's talk about parameter efficient tuning for pre-trained models. This is a method designed to fine-tune large pre-trained models while keeping additional trainable parameters to a minimum, allowing for improved training cost efficiency. There are various approaches to achieve this, but one of the most widely used methods in both recent research and industry is called LoRa and its variants. LoRa has become a key technique for parameter-efficient tuning, and it plays an essential role in many modern AI applications. Let's take a closer look at how it works. LoRa represents the change in the model's weight, which is typically an n by m matrix, as a product of two smaller matrices. What's unique about this approach is that only these two smaller auxiliary metrics are trained. By doing so, LoRa significantly reduces the number of trainable parameters, GPU memory usage, and overall computational workload. This makes it possible to fine-tune models much faster and more efficiently. Now, let's talk about continual learning and how it differs from traditional machine learning. In traditional ML, models are trained once on a fixed dataset and then deployed without further updates. However, in continual learning paradigm, the model is trained incrementally as new data arrives, making it possible to adapt continuously to new tasks or knowledge over time. Continual learning deals with data arriving in discrete chunks or batches at specific time points, such as AI model updating with new information. This is in contrast to static dataset in traditional ML. In the continual learning paradigm, recent research primarily focuses on enabling the sharing of knowledge arriving at different times, while mitigating catastrophic forgetting, where new information overrides prior knowledge. In summary, continual learning is about evolving models that can continuously learn and adapt, ensuring they stay relevant in dynamic environments. Now, let's discuss imitation learning. Imitation learning is a learning paradigm for behavioral tasks where a model learns to perform actions or tasks by mimicking expert demonstrations. As illustrated in the diagram, a human operator provides task demonstrations, or sometimes code or algorithm can provide it. And these expert demonstrations are then used to train an autonomous policy which translates task space commands into robot control interface, so-called actions. And ultimately, these result in a deployed robot capable of performing the demonstrated tasks, such as manipulating objects or interacting with its environment. Imitation learning is particularly effective in scenarios where designing a reward function for reinforcement learning is complex, making it a powerful method for training robots and other systems. To continual imitation learning, so-called CIL. CIL combines continual learning and imitation learning. In this paradigm, the data stream for continual learning consists of expert demonstrations for imitation learning. Tasks are continually evaluated using evaluation sets that reflect the requirements and changes at each point in time. As for the diagram, it represents our approach and scenario. We start with a pre-trained robot that is already capable of handling certain tasks in home environment. The focus of our approach is on adapting this robot to handle changes in the environment more effectively, enabling it to become a more versatile and adaptive agent. Through CIL, we aim to build an agent that not only learns from the past tasks, but also continually adapts to new challenges. Let's take a look at recent advancements in adaptive-based learning. Inspired by the success of large pre-trained models and extensive research on adaptive-based continual learning for sequential decision-making, particularly approaches that do not rely on episodic replay, our research is driven by two key questions. First, when and how can we achieve positive backward transfer similar to humans? Second, how can these tasks be managed flexibly in dynamic environments? To investigate these two key questions within the context of continual imitation learning, we identified three primary challenges. First, the requirement for comprehensive expert demonstration. This can be inefficient, especially for long-horizon tasks, and in some cases, it is simply impossible to collect expert demonstrations. Second, frequent task shift in non-stationary environments. Tasks are continually shifting in these dynamic settings, making it difficult to adapt to unseen tasks and maintain performance. Finally, actual privacy concerns. Accumulating knowledge in model parameters can raise privacy issues, as sensitive information may be implicitly retained with model. These challenges from the formulation of our work as we explore solutions to improve continual imitation learning in practical scenarios. We propose a framework called ISIL, which utilizes retrievable skills to address this problem. In each training stage, incoming expert demonstrations are stored as pairs, consisting of a skill prototype, which enables skill retrieval based on state similarity, and an adapter that learns the expert's knowledge. During evaluation, the model retrieves the appropriate skill based on the learned skill prototypes, and the current state, which is created from the observation and subgoal provided by the environment, and then infers the action. The figure demonstrates how the model operates and addresses the problem. Initially, when skills are first learned, if an incomplete demonstrations with missing parts are provided, task evaluation will fail due to a lack of necessary knowledge. However, if the next set of learned skills introduces actions that cover the previously missing parts of the state, then during evaluation, the model can retrieve skills from both stages to successfully complete task 1. Similarly, for tasks that initially seem likely to fail, previously learned skills can be retrieved and maximally utilized. In the same way, our framework ISIL can adapt to unseen tasks by combining existing skills, enabling it to solve long-horizon tasks without additional training. To evaluate the model's performance, we designed 3 scenarios based on the Franca Kitchen simulator and MetaWorld environment simulator. Each continual learning scenario includes 20 learning stages. In complete scenario, each task receives a full demonstration. In semi-complete scenario, a single task's demonstration is split into 2 separate instances. Finally, in complete scenario, is similar to complete scenario, but all tasks receive only partial demonstrations. It means that there's some missing parts on the expert demonstrations. Here, the semi-complete and incomplete scenarios specifically test the model's ability to share skills across different stages and tasks. This page shows the task metric we used, called the goal conditioned success rate, in short GC, in the context of long horizon tasks. A long horizon task is designed to solve multiple sub-goals in sequence. As shown in the diagram, the task consists of 4 sub-goals. First, interact with a microwave, and then use the kettle, and turn on the top burner, and finally slide the cabinet. The goal conditioned success rate evaluates the ratio of successfully completed sub-goals in the defined sequence. This metric is crucial for measuring the effectiveness of a model in tasks requiring multiple steps, where failure in one sub-goal impacts the overall outcome. By focusing on GC, we can better understand how well the model performs in executing complex sequential tasks. Here are some examples to better understand the goal conditioned success rate. On the left, the task involves 4 sub-goals, as I said. In this example, the model successfully completes the first 2 sub-goals but fails on the third. As a result, the GC score is 0.5. On the right, the model performs better, successfully completing the first 2 to 3 sub-goals but failing on the fourth. This gives a GC score 0.75 or 3 out of 4. And again, the goal condition success rate is a critical metric because it reflects not just the total number of sub-goals completed, but whether they were completed in the required sequence. The sequential dependency is essential for evaluating performance in long horizon tasks. And here are the metrics we used in continual imitation learning based on GC. While the detailed formulas can be found in the paper, I'll focus on explaining the key concepts here. FWT calls forward transfer. This metric assesses how well a model learns new tasks by leveraging a prior knowledge. And BWT, backward transfer, this measures the impact of learning new tasks on previously learned tasks. And a negative value here indicates catastrophic forgetting occurs, where the model's performance on past tasks deteriorates. And AUC, area under the curve, this represents the average performance across all tasks and stages, giving an overall view of the model's effectiveness. The visualization here demonstrates how these metrics are evaluated across successive tasks, capturing both the learning of new tasks and the retention of previous knowledge. These metrics are critical for understanding how well a model performs in a continual learning setting. Also, all metrics are calculated by GC, as I said. In our experiment, it still outperformed conventional adapter-based continual imitation learning methods with solvable information. And they are achieving significantly higher AUC scores overall. Furthermore, in scenarios where unseen tasks are introduced, it still demonstrated a high performance to these unseen tasks. Additionally, regarding privacy issues, it still demonstrated performance advantages even in an environment where unlearning tasks are required. It still remains robust in incomplete settings. And it also effectively handles the unlearning requests. Similar to our approach, methods that can separate models by task or skill have the advantage of combining effectively with unlearning techniques through the parameter deletion. And this is our conclusion. Our approach still brings several advancements, offers high flexibility with enhanced bidirectional transfer for the knowledge sharing, and adapts to unseen tasks by leveraging existing skills. We've also developed a simple yet effective learning extension within continual imitation learning. In summary, it still pushes the boundaries of continual imitation learning with adaptability, robustness, and efficiency at its core. Looking for the future, we see two main directions for SL and adapter-based continual learning systems. First, in generalization, combining model merging and task arithmetic could be a promising directions. For example, we may combine two model parameters, in my case, two adapter parameters, to create more robust task model like adapter for novel tasks. And second, in efficiency, refining caching algorithm for more efficient retrieval could be effective. It can reduce the retrieval time for our framework. And this is end of our slide. Thank you for your time.